Hello everyone, I'm Jingyu Liu from the AIMC Lab, School of Information, Renmin University of China. Today, I'm pleased to share our group's latest progress on sketch animation generation, titled Multi-Object Sketch Animation by Scene Decomposition and Motion Planning. You can find the link to our project page at the bottom left corner of this slide. The sketch animation task aims to transform a static sketch image into a dynamic animated sequence. In this paper, we focus on multi-object sketch animation, which deals with complex scenes involving multiple interacting objects. As shown in the example on this slide, our method can animate a sketch scene such as a man shooting a basketball. First, let me introduce the background. A sketch is a quick and abstract representation of objects or scenes, and it appears everywhere in our daily life. Therefore, understanding and analyzing sketches is both meaningful and valuable. Since a sketch is also a type of image, many computer vision tasks have been explored in the sketch domain, such as retrieval and segmentation. In our research, we are particularly interested in the task of sketch animation. We briefly review the development of sketch animation. Early works focused on developing tools for human-driven creation, enabling people to make sketch animations manually, but requiring extensive manual intervention. To reduce human effort, subsequent methods introduced additional inputs, such as videos or skeletons, which alleviated but did not eliminate manual involvement. Recently, driven by the success of diffusion models in video generation, new methods have been proposed that can generate sketch animations using only a static sketch and a text description. Two representative works are LiveSketch and FlipSketch. LiveSketch requires no additional training data. It employs Score Distillation Sampling, SDS, to iteratively optimize the animation process based on a pre-trained text-to-video diffusion model. In contrast, FlipSketch adopts a training-based strategy, converting a sketch into a noise vector via DDIM inversion, and then using a fine-tuned T2V diffusion model, trained on synthetic data generated by LiveSketch, to produce the animation. LiveSketch operates on vector sketches, whereas FlipSketch focuses on raster sketches. While both achieve impressive results in single-object sketch animation, they fail to generalize to multi-object scenarios, which motivates our work. With our research goal established, we identified two key challenges in multi-object sketch animation: 1. Object-aware motion modeling, and 2. Complex motion optimization. To address these, we proposed targeted solutions. For object-aware motion modeling, we utilize large language models, LLMs, to enable object-level motion planning and motion modeling networks. For complex motion optimization, LLMs are employed to decompose complex motions into simpler submotions, which are then optimized separately. In summary, our approach follows a clear principle: divide and conquer. We next discuss the choice of sketch representation. In this work, we adopt the vector sketch format. A vector sketch consists of multiple strokes, each represented by a cubic Bezier curve defined by 4 2D control points. Compared with raster sketches, vector sketches are resolution independent, more compact, easier to edit, and more stable. As illustrated in the figure, both our method and LiveSketch, which use vector sketches, generate stable and consistent multi-object animations. However, FlipSketch, which adopts raster sketches, often produces unstable motions with noticeable object deformation. Before introducing our proposed approach, we briefly describe LiveSketch, which serves as a reference method. LiveSketch takes vector sketches as input and formulates sketch animation as a sequence of stroke control point motions. An MLP is employed for motion modeling, and a pre-trained text-to-video diffusion model is used to compute gradients for updating the MLP. This optimization process is iterative, continuously refining the animation. The MLP-based motion modeling consists of two branches. A global motion branch, which handles overall transformations such as translation, scaling, shearing, and rotation. And an internal motion branch, which models the movement of individual control points. We propose MoSketch, a training data-free and optimization-based framework for multi-object sketch animation. MoSketch consists of 4 modules. 1. LLM-based scene decomposition. 2. LLM-based motion planning. 3. Multi-grained motion refinement, and 4. Compositional SDS. The LLM-based scene decomposition identifies objects, extracts their spatial locations, and decomposes complex motions into simpler submotions. These results provide the foundation for subsequent modules. The LLM-based motion planning employs a large language model to generate coarse-grained motion trajectories for each object. Next, a motion refinement network is introduced to refine the object-level motions and to model fine-grained internal movements. Finally, the animation is generated through compositional SDS, where the optimization process is applied individually to each decomposed motion component. In our MoSketch framework, large language models, LLMs, play a critical role. Before motion planning, we perform scene decomposition, where we identify the objects in the sketch and obtain their bounding boxes using grounding deno. In the subsequent motion planning stage, the LLM generates a bounding box trajectory for each object, describing its movement across frames. We observe that introducing explicit reasoning before motion generation, letting the LLM reason step by step, significantly improves the quality and consistency of the planned motions. Our multi-grained motion refinement module adopts a 2-branch structure, similar to that in LiveSketch, but with key improvements. In our design, the upper branch models object-level motion rather than the motion of the entire sketch. This branch acts as a correction network, refining the coarse motions generated by the LLM-based motion planner. Before the 2 branches diverge, a transformer-based message passing module is introduced to capture interactions among multiple objects. The positional encoding in this transformer is a polar coordinate-based relative positional encoding, which we specifically designed for vector sketches to better represent their geometric and directional properties. We conducted experiments on a newly created dataset of scene sketches. Since no public dataset exists for multi-object sketch animation, we first generated single-object sketches from real images using CLI Passo, and then composed and refined them with a vector graphics editor to form realistic scene sketches. In total, we built a test set of 60 scene sketches, covering diverse real-life scenarios such as sports, dining, transportation, and work. Additionally, we release a larger set of 500 scene sketches on our GitHub repository. Each scene sketch includes semantic segmentation and coarse motion planning, enabling quick reproduction and further exploration by the community. We compare our MoSketch with 4 representative baselines: LiveSketch, FlipSketch, and 2 image-to-video diffusion models, namely CogVideoX and DynamicCrafter. Experimental results show that CogVideoX, DynamicCrafter, and FlipSketch often generate noisy and inconsistent motions, failing to maintain object stability in multi-object scenarios. LiveSketch, on the other hand, produces nearly static animations with minimal motion. In contrast, our MoSketch achieves the most stable and realistic motion, demonstrating clear advantages in both motion quality and scene consistency. Here is the gallery of results generated by our MoSketch. It can be observed that the generated sketch animations are highly dynamic and visually engaging, exhibiting smooth and coherent motions across multiple objects. These results highlight the effectiveness and creativity of MoSketch in generating vivid and realistic sketch animations. This slide presents the ablation study of MoSketch. Removing any single module leads to a noticeable degradation in performance, resulting in nearly static external movements, missing internal object motions, semantically implausible interactions, and loss of fine details. These observations verify that each component is critical to the effectiveness of the proposed MoSketch framework. Experiments on the Skoko hand-drawn scene sketches and the LiveSketch single-object sketches demonstrate the strong generalization ability of MoSketch. The model effectively repairs imperfect hand-drawn inputs and produces large-scale, coherent object motions. This confirms the robustness and versatility of our proposed approach across different sketch domains. Our method supports text-guided controllable animation generation, enabling different animation results from the same sketch. However, several limitations remain. 1. Incorrect point assignment may affect animation quality. 2. Severely inaccurate motion planning cannot be fully corrected. 3. The final results are constrained by the pre-trained text-to-video diffusion model, which limits the range of achievable motion types. Thank you for watching and for your attention. We hope our work, MoSketch, inspires more research on sketch-based animation generation.